Okay, as many of you know, my name is Christopher Roller. I'll be giving a talk on my thesis entitled The Frequency of Winter Weather Regimes in the U.S. Northeast as an Indicator for National Climate Assessment. I just want to start with an overview here, just go through some of the methods, some results, and some discussion, as well as the be-all and all that we're looking for here. So, want to tell you what the K-means program was, which is sort of going to take each individual daily weather map and sort it into a number of distinct weather patterns. Then we need to be able to identify if those 5 distinct weather patterns are important enough, are distinct enough, and that's what the classifiability index, or CI, does. I'll show the results from that. Then after we run the K-means and the CI, we get something called weather types, which are your distinct weather patterns. I'll refer to those later as WTs. And then I'll get into a discussion of teleconnections, storm tracks, precipitation, energy demand correlated with the WTs. And those individually are taken from the individual days within each mean weather type. And then from looking at teleconnections and storm tracks, I want to propose a possible index for storminess. So just to kind of get into what K-means is here, imagine a phase space with X and Y plane, and then also imagine these pink points here are weather patterns. The next thing I'm going to do is I'm going to initialize 3 random points within that plane. These points are going to eventually be our weather types. They're called centroids or cluster centers at this point. So then when I try and match each of the individual data points to a particular cluster, pink to pink, green to green, Dr. Colby, I believe the green one that you have on yours is actually still gray. I changed it on here. So just a heads up. So then the next thing we want to do is we want to move that cluster to the center of those data points. Remember, we want these clusters to be the mean of all those daily weather patterns. So that's what it does there. So then we want to reassign those points based on where those new cluster means are. And so these ones are now going to be reassigned based on where that new cluster center mean is moved. So then we want to recalculate the mean again based on those new the new movement of those patterns. And so that happens again. Now, each of those individual movements of the cluster mean is going to be heretofore called a partition. And that becomes important when we look at our classifiability index. What it does is each of those individual partitions or movements of those centroids, when you're comparing each of those individual ones, if the centroid does not move, the partition is given a 1. If it does move, it is given a 0, so that the percentage, the resulting number you get is an average over all of those 1s and 0s, and that is what is plotted here in these 2 plots. We ran this data on 2 different types of output. One was including the annual mean of, and the data we ran in this case, and most of the cases, was 850 winds over the winter period of DJF. And so just to kind of give you an idea of what's going on in these plots, we ran the K-means program itself from between 2 clusters to 20 clusters. And when it is run that way, you get a percentage, as I was talking about before. So when you have just 2 clusters, it is fairly easy to split the data into 2 separate piles. So that's why you should get somewhere very close to 100% in that case. Now, as you're getting into a larger number of clusters, it shoots down pretty fast to 3 and then 4 clusters. When you see a large rebound, that is the number of clusters you should probably end up using because it's going to be one of your higher numbers that you're going to get out of the data. And then it's going to drop off, and then it'll ramp back up again as the number of data points that you have, daily weather patterns, equals the number of clusters you're testing for. Now in this case, our annual cycle data and the anomaly data had the same number of clusters, 5 in this case, so that's what we're going to run with. So this is the results we get. We get two types. The one on the left is the annual cycle, the one on the right are the anomaly weather types. Just to kind of go over what we have in each of the different weather types here, we see WT1, 2, 3, 4, and 5 in the BJF mean in the bottom right-hand corner. Weather type 1, we can see a ridge in the circulation just off of the southeastern United States with a trough over central United States, and actually a low-level jet carrying moisture up far north into the southeastern states. WT2 has a weaker low-level jet from a weaker ridge. Your trough is now offshore, and your trough in the western United States and central United States is further west than WT1. And WT3, now we have a trough just centered off of, just southeast of southern New England, with a ridge over western or central United States. And WT4 now has the trough over central United States and eastern United States. And then we have the ridge offshore and a flow that is east or southeasterly there. WT5 is distinct from most of the other ones in that there is a upper level low generally in southern Canada. You also have northwest flow to the west of that, southwest flow to the east of it. And the DJF mean is down here. Now, when we pull the DJF mean out of all of the weather types, you get what we have here are anomalies. We've also plotted the anomaly winds. In this case, the anomaly winds give us low pressure and high pressure centers, which is sort of like almost eddy transports, you might consider. So in this case, we have a high just south and east of southern New England, and on the northerly flow, you tend to see negative precipitation anomalies. On the west of that high pressure center, you can see positive precipitation anomalies, and that is on southerly flow as well as easterly flow along the eastern seaboard. In WT2, we have, again, the northerly flow giving the negative precipitation anomalies. You can see a, let me double check here, yeah, that is a low pressure center in WT2 just off of the eastern seaboard, south of New Brunswick, east of Maine. And WT3 is almost the exact opposite in where the precipitation anomalies occur as well as the pressure centers, such that where the precipitation occurs, you have the opposite wind and the opposite type of pressure system. Same for WT4 to WT2. In WT5, it is fairly similar to the old WT5 in that WT5 has basically the same flow. And you still have your upper level low distinctly in southern Canada there. You'll also notice that we have low precipitation anomalies over the states and a lot of the ocean. The only place you'll see the higher precipitation anomalies is over the water in the Gulf, parts of Texas as well. There are slight positive precip anomalies. So one thing I should mention here is that WT3 and 4 are the highest precipitators, and WT1 and 2 are the lowest in southern New England. So what we were able to do was, within each individual weather pattern or weather type, there were dates in there. So when you take all of the dates and grab, this data was from mirror data from NASA, when you grab all of those dates and their temperature on that day, you can then recreate the same exact mean for the weather types here. So these are the exact same annual cycle on the left, anomalies on the right, same flow patterns, just now we have temperature plotted. And why we've zoomed in on this left column here is just because pretty much all of the annual cycle looks something similar to this DJF map here. So we thought it would be easier to see if we zoomed in and give a smaller interval for Kelvin than what we had before. What we can see here is that WT4 and 1 are the warmer ones, WT2 and 4 are the colder ones. 2 and 3, excuse me, and then that WT4 is the warmest. WT5 is fairly close to the mean again. So we can also see that southerly winds give us our warming winds, and cooling winds are given by the northerly winds. I believe that's all I wanted to say on that. Okay, so then the next thing we want to look at here is our sort of like how do we go from one WT to another WT. If we start with WT1, for example, what comes after WT1? Weather type 1. And so that's what this top table is telling us. That's the sort of frequency that we have going on there. So if I start with weather type 1 in the vertical column here, that tells me which weather type is coming first. Then if I want to see which one is coming next, I look across the horizontal here. So WT1, the next one that comes after that is WT1 based on this 187 more occurrences than every other one in that row. And so that's how that works. Now, the next table that we have here is this normalized percentage. Basically, the point of that was we see all these uneven number of totals here. And I wanted to eliminate the factor of having uneven number of totals being a reason why we would get some discrepancies in teleconnections or something like that as we're manipulating the data. So as we're going through it, basically how I came up with this was if I take the total, or the matching up of 1 and 1, or 187 here, divided by 593, which in that case was 31.5%, and then I take the 593 divided by about 2,700 number there, that gives me about 21 or 22%, 21.97. So when I divide 31.5% by 22%, we get somewhere around 143%. So I know that in this case, 143 is one of the higher numbers. It also tells me that it is a persistence forecast, so that when I have WT1 occurring first, I should have a higher percentage of WT1s occurring after that. Same for WT2, that higher number of WT1s occur after WT2, excuse me. And then WT3, a higher number of WT2s occur after it. WT4, a higher number of WT3s occur after it. And then for WT5, a higher number of WT5s occur after that for another persistence forecast.
Chris,
Sure.
just so I understand, so does 100 here mean if everything were 100, it means that there is an equal chance of everything? Is that?
So it's that the 187 divided by 593 equals the 593 divided by 2,700. So it would basically say that the proportion of the occurrences within that WT1 is the same proportion of WT1 itself to the total number. That's the best way I can explain it.
Yeah, 100 means the following weather type has no difference could be followed by anything.
Right, so as if it was evenly distributed. Yes. Okay, so
it's over 100 means it's more likely to be followed by this.
Okay, and under 100 is less likely.
Less likely if it's just
than an even distribution.
Yeah,
Okay.
even distribution.
And wait, can I ask a question there? Are you looking at the weather type like just for each day? So you're saying when you say what follows, you mean the following day?
Yes,
the
it's
second
daily.
day?
It's
Okay.
daily. One day, one weather type.
Okay.
Sorry.
So that 187, that's 187 days actually. Yeah, that's
Yeah.
many years.
Okay.
Winter season.
Oh,
Daily.
I'll write down my question.
So then one thing you'll notice is that as we're looking across here, we don't see any WT4s that are colored blue. The only time, so what my next method was, okay, so if I want to see what then creates WT4 second most often, I need to go down here. So I need to follow the down, which is what this third table tells me. So I need to see what comes before WT4, and in this case, if you go to the left, we now see that WT1 occurs most often before WT4 for our percentages and even up in this frequency table. So we can see sort of a split in that case, that WT1 could either go to 1 itself or to WT4, and remember WT4 was sort of the trough right over the right over the southern New England area. And I'll sort of show the progression of that in a few plots coming up here. And again, WT2 through 4 has the same sort of persistence, and WT5 again is the same persistence. So then the next thing I wanted to do was come up with each individual teleconnection. So for each individual date, NAO has been it's been projected on each of those individual days in a given number. So that if it is a positive NAO, and let me get into this too, the NAO is characterized by a high or a low in Greenland, or a high or a low just south of it. So that if you have a low in Greenland and a high just south of it, you have flow that goes in between, because flow around the low flows anti-clockwise and clockwise around the high. So you get sort of a coupling of winds in between. So the trough can't dig as much, which means that the storms can't get as strong, and then they get pulled out to sea early. And then the opposite for the negative NAO, in that when you have a high pressure system over Greenland and a low the other way, south of it, the east winds between the two actually keep the storm track to the west and allow the trough to dig a little bit more. And so in this case, when we're running the same normalized percentages in a similar way we did it for the persistence forecast, we can see that positive NAO corresponds more often to WT1 and 5, which makes sense because those were the, actually never mind that. And then negative NAO corresponds most often to 2 and 3. Neutral NAO corresponds most often to WT4. And then the next teleconnection we looked at was the AO, Arctic oscillation, and that is characterized by positive or negative geopotential heights over the Arctic. So that in the negative AO, you have positive geopotential heights over the Arctic, which corresponds to negative geopotential heights over the eastern seaboard, and cooling temperatures over the eastern seaboard. And the opposite for the positive AO. So that positive AO was corresponding to 1, 4, and 5 most often, negative AO for 2 and 3, and actually, I'm sorry, WT1 corresponded to neutral AO most often, but you can't rule out AO positive with that being so close, almost it's still statistically significant. The next teleconnection we looked at was the PNA, and this is characterized by meridional flow, so that you check the opposite sides of the United States. In the east United States, if you have negative geopotential heights, that corresponds to a positive PNA, because you also have to have positive geopotential heights along the western side of the United States, and the negative PNA is opposite. So in this case, positive PNA corresponded most often, or drove most, WT2 and 3 occurred most often in positive PNA. As you can see here, negative had WT1 and 5 occur most often, and then neutral PNA had WT4 occur most often. And then the last teleconnection we'll look at is ENSO, and this is characterized by positive or negative temperatures between plus and minus 5 degrees of the equator latitude. And so if it's warmer temperatures, that's an El Nino. If it's colder temperatures there, it's a La Nina. And we get positive ENSO most often creating WT2 and 3. Negative ENSO or La Nina creating most often 1 and 5. And WT4 occurring most often in neutral ENSO. But negative ENSO is actually fairly close in the percentages there. Okay, so the next thing we wanted to do is sort of break down each individual weather type. So if I take the anomaly plot from each weather type itself, and then take the temperature anomalies that are most often seen in those teleconnections, and these are actually from North Carolina State University. So in this case, for weather type 1, we see more often the warmer temperature anomalies along the southeast and eastern seaboard there. And actually this WT1 plot corresponds very well to the temperature anomalies you see in this plot here. So that was interesting to see. So then for WT2, we had the opposite teleconnections basically, so that the colder temperature anomalies occurred along the eastern seaboard here, and they also occur in the other teleconnections. The other thing that I did was I took some of the dates within the weather type itself and threw them into the anomaly creator on the SRL PSD page. Now, the one thing I should throw in here is sort of a caveat is if you're not taking all of the dates, it can tend to kind of give you a fake answer. So this may not necessarily be totally correct, but you can still see here warmer temperature anomalies, not as strong as a positive N cell, but still a decent N cell going on there.
Chris,
Sure.
could you point to those figures and then corresponding a little bit more detail, you know, like point to whether it's positive or negative?
So basically the point was is wherever you see the cold temperatures here in each of the teleconnections, you're also going to see the colder temperatures along the eastern seaboard, mainly because in the positive P&A you have the lower geopotential heights along the southeast there, which is also matched up to in the weather type temperature anomalies. In the AO, you tend to have cooling temperatures coming in from the Arctic on northwest winds. And then here you have cooling temperatures as well, not necessarily northwest winds, but remember this is the anomaly temperature plot, so the flow is not necessarily what matters there. And then again, you have cold flow coming into the United States again in the negative AO, similar to what you see in WT2 on the eastern seaboard there. And WT3 is actually fairly similar, so that where you have cold temperatures coming in again on each of these teleconnections, you also have it along the eastern seaboard. The one thing that is fairly different is that you actually have more warming temperatures in WT3 there, where the other teleconnections do show the cooling temperatures, colder than normal temperatures. And then the last thing again, ENSO is warmer there.
Quick question, Chris. So, the plot on the lower right, that's from daily data or monthly?
Daily. So basically, and I should mention this too, when I had 3 weather type 3s occurring or more, I grabbed the middle one, so that in that case I knew that was most often going to be like the best chance I get at a WT3 type forecast. So if you have fluctuations within that weather type thing. So when I plotted, and this only takes about 20 days, whereas I had about 500 days to create the mean for each weather type, and that's why it was sort of not the greatest way to come up with it, but the best I could have at the time.
Well, I think what you're seeing is just to state the obvious. It's just that there's a sort of a modest connection with ENSO.
Yeah.
So you would expect to see modest SST anomalies when you composite that way.
Great.
I don't know if it's worth doing, but I think if you took the months, or maybe even the seasons that had the most weather type 3s, which would be a totally fairly different kind of calculation, you might see a better
Okay.
SST anomaly.
That's a good idea. Anything else? I'll continue on here. WT4 was a little bit more interesting in that a lot of the teleconnections we had were actually neutral. And so I'm just going to focus on those that sort of vary away from the neutrality. So in this case, again, where you have the warming temperatures, that corresponds with the positive AO as well as the positive geopotential heights. It was also interesting in this one to see a negative ENSO anomaly pretty strong compared to the other ones, which were still in like the first to second green. This is now getting into purple in the anomaly plot down below. So then the last weather type we have here is 5. This was, again, with the upper level lows. You have northwest flow coming into that region. unfortunately, for that, where you have the cold temperature anomalies, it doesn't really match with the tower connections. Sort of unsure why that was, even though you still had it as that teleconnection. It may, yeah, I'm still sort of unsure of that. So then to kind of throw it all together, these are plots I put together using the anomaly, low pressure and high pressure centers, and then the 850 flow. And so basically we see the progression from 1 to 2 with 4 and 3 in the middle. So 1, 2, 3, 4. So that you have your negative P&A here, your positive P&A with a high pressure block, same here, and then still your positive P&A there as well, slightly offshore for your positive P&A. One thing you'll also recognize too is that from 1 to 4 your trough is deepening, and 4 and 3 have similar depth to the trough, and when your trough deepens you tend to have your stronger lows, and then it'll pick back up in weather type 2. So you can almost see a movement of the low as you're going through. And the one other thing I did want to mention too is that the easterly to southeasterly flow that we saw there, it almost sort of hints maybe a development low sort of creating, so that where you have a northeast track of that low going in almost like a parent low, you get sort of a development low occurring east of the Carolinas, as does happen sometimes. And I'll kind of show a better plot of that coming up later. And then I'll talk about WT3 in that sense as well. Okay, so now here's storm tracks. The next few pages are actually data from Laureate. She put these together for me based on the dates that I gave her. Basically what it is at each 4-hour time step, you have storm track positions that are plotted. And so that wherever you see the higher densities, you can pretty much say that there's a definite chance of the low pressure center being there. And so just some of the things we can see in the progression here is where we had the low occurring minus 24 hours from time equals 0 of the date of that weather pattern. It then sort of moves in a clockwise motion around the northeast in that one, in WT1. WT2, we can sort of see a low pressure center that then evacuates the coast. WT3, we can see sort of storm tracks that originate down in the Gulf and then slowly move their way up the coast. WT4, we can sort of see movement, storm tracks in the northeast direction this way, as well as storm tracks movement towards the southeast that way. And then a strong density of lows around the Great Lakes and then moving northeast, as well as sort of a disappearing in the plus 24-hour increment of that Great Lakes low and movement of the low to the northeast. So that was sort of interesting to see. You'll also remember in WT5, the upper level low, which then slowly moves east, showing the storm track densities disappearing on plus 24 there. Okay, so then the next thing we have here is we have precipitation. So again, from each of the individual days, we have precipitation that comes from that. And what it was is all these individual stations were chosen because they did not have 1% of their precipitation missing. And then they were classified as coastal or inland. So blue is coastal and green is inland. Now, when we take a look at the percent or the number of days of precipitation at all occurring in each of these weather types, we see weather type 3, 4, and 5 having the most amount of precipitation days. Now, when we take a look at just the precipitation itself, we see that WT 3 and 4 are now the two higher ones for the higher precipitation, whereas WT 5 has now dropped. And probably what's going on there is that you have more days here of less precipitation, and then again more days of 3 and 4 but of higher precipitation. going on there. And then weather type 1 and 2 seem to be the smaller precipitators as far as weather types. And then the next thing we have here is we've taken not only the top 1%, or the stations that are not missing the 1% of precipitation, we've also taken the highest, the top 1% of precipitation at all, and seen which weather types those occur in. And we see in that case that weather type 3 and 4 are where those occur most often. So it would make sense that those would tend to have the more extreme, the highest precipitation, and that actually translates to the storm tracks plots. So this is extreme precipitation and the low pressure center that occurred on that day. You could then consider creating that precipitation. And it is a lot along the northeast coast, and you can still sort of see like almost a parent low in weather type 4 there. A small dot in southeastern Missouri. On weather type 1, not much significance there, however. Okay, so then when I plot just the extreme storm tracks in the progression, you can again see sort of, and actually here's where I want to compare it to Atlantic coastal redevelopment from Coast and Ussalini, as well as the Gulf originating ones. So this plot here seems to correlate most or best with weather type 4 as far as where the parent low occurs, the storm tracks. The one thing I did not see, however, is when I took these dates, the ones that are within my time frame of 1980 to 2010, they were kind of evenly spread, so that they occurred almost even between all of the weather types, including 1 through 5. And so that would kind of discourage the possibility of having these types of storm tracks occur in one single weather type. And here's the other one. So this Gulf of Mexico originating one for weather type 3. You can sort of see some storm track occurring around the Atlantic region, the Gulf region, and then moving up the coast. And the extreme precipitation. And the same was for this as was for the development, that it was still, again, evenly spread, which is sort of weird, interesting to see. So then I showed before we had the temperatures, anomalies, and annual cycle. Basically what I did was I then took those dates within the weather types and tried to correlate, if I have more weather types, does that mean I have a higher natural gas demand, and then the next one is electricity demand. The one WT that had the highest correlation between the two is weather type 1. Now unfortunately with weather type 1, that is the one that had the warmest temperature, or one of the warmer temperature anomalies. So it doesn't make any sense. Normally you would think in the winter time you would want colder temperatures to have a higher natural gas demand. So that was kind of also something we couldn't quite come up with or clarify a reason why.
Because they're the mean temperature.
Yeah, yeah. And then the same for the electricity we did. In this case, weather type 5 had the highest correlation to frequency of weather type. Again, this is one of the warmer ones, especially along the northeast region. This one, you could probably have a better idea, because you remember that temperature anomaly plot had the northwest winds into the region. It was cooling except for southern wind winds. So, and this was around that upper level low. So maybe that has something to do with it. So when we throw all those things together, we decided to use weather type 3 and 4 as our sort of tracker of storms across the entire time frame. Now when I take the average of every single year of the number of weather type 3 and 4, I get a mean of about 28 and 2/3 of the number of storms. And then it also is increasing, as this black line shows, at about a rate of 0.14 storm per year in that 31-year period, but 30 winters. Okay, so now as far as my conclusions go, weather types give a good, sensible idea of general weather patterns. It is the average of many dates, so all those dates are important. We took a look at the teleconnections, and those papers that I've referenced in my thesis give a good idea as far as what they do to move the storm tracks, and where the lows go because of those storm tracks, or because of those teleconnections. I should also say at this point too that while you have the teleconnections sometimes creating the lows and different weather patterns, you can have it the opposite way, that where a low moves, it can actually influence the teleconnection, so it's kind of a positive feedback. We also saw that there are storm tracks showing hints of major storms, the two major types that Kosin and Mussolini talked about, precipitation as well. And then the energy demand also has some correlation with WTs. Unfortunately, they were not statistically significant, so future work has to be done with that. And then from the index, we can see which WTs have the highest, or the index uses the WTs with the highest precipitation and the strongest storm tracks. And so that's what we've used to kind of gauge storminess. And the last thing I've shown here is a table of all the teleconnections, precipitation, and annual cycle temperature, and sort of the steps and progression and the phase and which ones were warmest and coldest. Now the last thing I've done is to sort of help the storm track talk there is taking a look at the Thesis, the Northeast Snow Impact Scale, which was also done by Kosin and Mussolini. And basically they measured the progression of the storm track, which brought some of the heaviest snowfall and had a huge impact on the Northeast in one database. So the amount of snow, how long the track was, those are the things that that database measures. And those that had the highest was good to see actually occurred within our progression. So weather type 2, 3, and 4, and so those ones had the highest within that database. And just a reminder that that Thesis scale includes the entire range from the beginning of when the snowfall happens to when it goes offshore or the snowfall stops. And so that's it.
Perfect, climbing.
Okay. Be glad to take any questions we have.
Any questions?
Yeah, we might start with questions from the general audience, and then we'll boot everybody else out.
Please.
Where did you get your data for the energy usage?
So it was from ISO&E, and then there was another one that dealt with electricity. They're sort of government agencies that put that stuff together.
Those are per capita?
So that I am not sure. Do you know, Dr. Barlow?
No, I think their net usage, the electric is daily usage for New England, and then the gas is monthly, I think
So
also.
they're 30 years of data, so...
No,
Oh, I thought you said it was 1980.
Yeah, that I should specify. The electricity, I believe, was 10 years from 93 to 2000, or from 93 and on, I'm sorry, so it would go to 2010 for me. And then the natural gas, I believe, was 2003, or the other way around, one of those two. One started in 93 and the other started in 2003. So it wasn't the entire time period of my weather type sections.
Okay, and they were just Massachusetts? I missed that one area.
New England.
All of New England? So does that include New York to you guys or not?
So that doesn't know.
Okay.
Yeah, I had a similar question along with that too. So were those two the more common modes of home heating, the electricity and natural gas for this region? Like, was that why you chose those?
Yeah, wood is kind of harder to measure because you'd have to measure, first of all, the sales of wood pellets and stuff like that, and then to have it correlate or track to where you actually put it in your house is something that's hard to track. So you can measure it on the house as far as the meters go with natural gas and electricity. So that's why those are the two most popular.
It's a bit of a question of data availability, right? What kind of data can you actually get your hands on?
My question's a little offbeat here, but you mentioned El Nino.
Yeah.
I take a look at that, and that is just an enormous amount of energy. Does anyone know what causes that?
So it has a lot to do with under the sea, but it basically you have an oceanic Kelvin wave that sort of moves, propagates across the ocean, and eventually and it's a warmer temperature area, and that can actually rise to the surface via westerly movement of that wind to sort of counteract the trade winds, and that usually happens spring and fall, that the trade winds tend to die, and that's sort of in general how that tends to work, to sort of move.
Well, but anyone knows what's causing the temperature rise in the first place? Is it an underwater volcano or?
Offhand, I'm not exactly sure.
No, I don't think anybody is. Okay.
No, I mean, but it's also, sorry, so in other words, you're talking about like a temperature rise in one location, but it's compounded by a temperature decrease in another location. I mean, the way I've always understood it is you get increased winds, that causes, changes in upwelling. It's not, and so, I don't know, I've always seen it as that. It's not, there's more energy in one place, but there's less energy in another, that you can continue to go with it.
Yeah, I think that's fine. There's a, like 30 or 40 years worth of research on El Nino, so there's a lot. But yeah, it's basically the ocean affects the atmosphere in the tropical Pacific, and the atmosphere affects the ocean, so they feed off each other. And as far as the atmosphere is concerned, rearrange where the tropical convection is. So I agree. It's not so much that you're adding energy, but you're rearranging it, which shifts the jet streams and therefore the precipitation.
Okay, thank you. That's probably an unfair question. Okay, that's all
Oh,
right.
any questions?
Yeah.